The Fast Fourier Transform accelerates digital signal processing by compressing calculation times from an n-squared mathematical load down to n log n. At the core of this processing is cyclic convolution, an operation that takes two sequences of data, shifts one, and multiplies them together to produce a third. Here, cyclic convolution is strictly linear algebra. Multiplying input vector v by dense circulant matrix C exactly matches convolving v with vector C. Substituting C's spectral decomposition splits this into three operators, f, lambda, and f inverse. The speedup relies on lambda, a diagonal matrix eliminating massive cross-multiplications. Computational scientists utilize the Fourier matrix F to achieve this diagonalized form, but that raises a structural question. Why does this specific set of sinusoids diagonalize circulant space? To prove why the FFT works, we have to look past the algorithms. The answer lies exclusively in the eigenstructure of a single primitive linear operator. This is the cyclic shift matrix, denoted as P. Notice the diagonal line of ones just below the main diagonal. In matrix multiplication, these act as an escalator, pushing input vector elements to the next position. A single one sits in the top right corner. This entry closes the mechanical operation into a loop. To observe these mechanics, we map a multiplication against an arbitrary column vector, x1 through x4. The multiplication executes, and the elements x2, x3, and x4 slide up exactly one position in the resulting column. Simultaneously, that top right entry grabs the initial x1 component and wraps it to the bottom. The input vector has been preserved, but its numerical sequence is shifted by exactly one index. This shift and wrap matrix defines the structure of all cyclic linear systems. The next analytical step is to find the eigenvalues that govern this specific shift operator. We start with the standard characteristic equation. We subtract the matrix P from lambda times the identity matrix and set the determinant to 0. For an n by n shift matrix, expanding that determinant collapses the calculation to a single polynomial, lambda to the power of n minus 1 equals 0. Rearranging, we find the eigenvalues must be numbers that, when raised to the nth power, equal exactly 1. To locate the solutions, we project this requirement onto the complex plane, tracing a unit circle with a radius of 1. The solutions are the nth roots of unity, plotting as evenly spaced points along the circumference. Each root is separated by an equal angle, mathematically defined as e to the power of 2 pi I over n, denoted by omega. The physical act of shifting data in a closed loop mathematically forces its eigenvalues to distribute in rotational symmetry in the complex plane. With the eigenvalues located, we now construct the exact eigenvectors that pair with these complex roots of unity. This core equation defines the relationship. Multiplying the shift matrix by an eigenvector x must simply scale that vector by lambda. Expanding the components reveals a strict cascading dependency. Because the matrix shifts data upward, the second component must equal lambda times the first, the third equals lambda times the second, and so on. Substituting these dependencies proves that every subsequent component is the next sequential power of the eigenvalue. By setting the first component to 1, the eigenvector format resolves. 1, lambda, lambda squared, down to lambda to the n minus 1. We then replace the lambda placeholder with the actual roots of unity, generating a distinct eigenvector for every root. Stacking these specific root of unity column vectors side by side produces a full square matrix. This precise assembly of eigenvectors is the definition of the discrete Fourier matrix. Any two columns within this grid are strictly orthogonal. Their inner product forms a geometric series of equally spaced angles that inherently cancel each other out to 0. The Fourier basis is the eigenbasis birthed directly by the pure cyclic shift operator. Having resolved the complete eigenstructure of the shift matrix, we can apply this mechanical logic to any general circulant matrix. A standard circulant matrix is built by taking a single row of data, duplicating it, and repeatedly shifting it cyclically to construct a full grid. We translate this geometric construction into algebra. Every circulant matrix is a sum of scaled shift matrices. This polynomial equation proves that the circulant matrix C is constructed entirely out of polynomial powers of the shift operator. A fundamental rule of linear algebra dictates that applying a polynomial to a matrix alters its eigenvalues, but leaves its eigenvectors untouched. Because C is a polynomial in P, any vector that is an eigenvector of P is mathematically guaranteed to be an eigenvector of C. Since the Fourier matrix successfully diagonalizes the base shift operator, it automatically diagonalizes every single possible circulant matrix. This returns us to the practical engineering application, cyclic convolution. Convolution is mathematically identical to multiplying an input vector by a large circulant matrix. Substitute circulant matrix C with its Fourier decomposition. Tracing right to left, multiplying by F inverse projects data into the frequency domain. At lambda, the dense convolution collapses into simple element-wise multiplication by eigenvalues. Finally, the leading F matrix maps the solution back to the time domain. The original matrix calculation demanded an n-squared computational load. This path bypasses that density, routing the operation through a diagonal matrix. Fast convolution in the Fourier domain is the mathematical consequence of projecting data into the native eigenbasis of circulant space.